Hello everyone. Today we're going to explore something that's crucial to modern computing security, an analysis of the Linux random number generator, or we just call it LRNG. This analysis examines how LRNG works, its vulnerabilities, and how it affects security in systems. This might sound technical, but I promise you'll see why it matters to everyone who uses technology. Before we dive in, let me ask you, have you used any online banking today? Played any games? Connected to Wi Fi? All of these everyday activities rely on random numbers of security. Why randomness is crucial in computing? Randomness is the backbone of cryptography, which protects everything from secure communication to password storage. Weak random values can be exploited to break systems. So, a strong random number generator is essential for maintaining secure systems. But how do computers generate truly random numbers? Let's talk about differences between true randomness and pseudo randomness first. When we talk about true randomness, we mean something that happens unpredictably in the real world, like radioactive decay. These are processes where the next event cannot be predicted, even if you know all the past events. On the other hand, pseudo randomness is what computers use. It looks random but is generated by an algorithm based on a starting value called a seed. If someone knows the seed, they can predict future outputs, making pseudo randomness less secure for critical applications like encryption. Computers follow set instructions and can naturally generate true randomness. They rely on algorithms to simulate randomness, but this isn't enough for critical tests like cryptography. So, think of it like rolling dice. When you roll physical dice, the outcome is random due to physical factors like air resistance and the way you throw. Computers need to achieve something similar, but they can't roll physical dice. Instead, the LRNG uses unpredictable events from your computer, like when you type, move your mouse, or access your hard drive. Computers gather entropy from unpredictable external events like mouse movements, keystroke timings, and disk activities. These sources help create randomness that's more secure for certain applications. To understand the security behind random number generator, there are three important concepts we need to cover: pseudo-randomness, forward security, and break-in recovery, also known as backward security. Let's break each one down. The first key concept is pseudo-randomness. This means that the output of the random number generator looks random to anyone observing it from the outside, even though the generator is using an algorithm. In other words, while the random numbers are being generated by a process to an external observer, they appear completely random and unpredictable. Next, we have forward security. This is a crucial property for ensuring past outputs remain secure. The idea is that even if an adversary learns the internal state of the random number generator at a specific point in time, they shouldn't be able to use that knowledge to figure out previous random numbers that were generated. Lastly, we have break-in recovery, also known as backward security. This is about protecting future outputs. Even if an adversary learns the internal state of the generator at a specific time, they shouldn't be able to predict future random numbers, as long as the generator gets refreshed with enough new entropy. Both forward security and backward security are crucial to protecting the integrity of the generator's output over time. ensuring that any breaches are limited to a specific point and don't compromise the entire system. The LRNG uses 3 pools of random data, kind of like 3 different dice cups, which are used to produce random numbers. Entropy is essential because it ensures the randomness of the output. The primary pool collects all the random events. The secondary pool provides high-quality randomness for critical operations, and the U-random pool gives us quick access to random numbers when we need them fast. The /dev/random provides extremely secure bits and may block the user until such bits can be generated by the system. The /dev/urandom outputs less secure bits, but its output is never blocked. It's like a chef gathering ingredients from various sources and mixing them together to create a unique dish. The pools mix these sources of entropy to create randomness. This is the process of entropy extraction. First, we need to initialize the status of LRNG, and we collect entropy from external events. Then we estimate the amount of entropy we collected, so we can update the entropy amount of each pool. Finally, we extract random bits from the pools. During system startup, the LRNG is initialized with predictable values, like the time of day, which can lead to vulnerabilities if not handled properly. For systems without strong entropy sources like hard drives, the LRNG's initial state can be weak, making it vulnerable to brute force attacks. To avoid predictability, Linux saved a 512 bytes random seed from /dev/urandom and shut down, which is restored at startup, ensuring the LRNG state isn't reset to a predictable value. Some Linux distributions, like OpenWRT, don't save this seed, making their random number generation much weaker and easier to predict after reboot. Imagine you're living a game midway. You save your progress before shutdown. The next time you boot up, you reload your saved game state so you can continue from where you left off, right? LRNG collects entropy from various events in the system to maintain randomness. This process is vital for generating secure random numbers. In a typical PC environment, entropy comes from sources like keyboard and mouse events, disk I/O operations, and system interrupts. Each of these events contributes random bits to the entropy pool. Each event generates 2 32-bit words, one encoding the timing and the other encoding the event type, like which key was pressed on the keyboard. On devices like routers, which lack keyboards or hard drives, the only source of entropy comes from network interrupts. This limitation can make the system's entropy more predictable, reducing security. While PCs have multiple entropy sources, devices with limited hardware can have weaker entropy collection, which affects the security of their random number generation. Next, let's see how entropy is estimated in LRNG. The role of entropy in random number generation is critical. It's the measure of unpredictability or randomness in a system. In the LRNG, entropy is collected from various system events like keyboard presses, mouse movements, disk activity, and network interrupts. The amount of entropy added to the LRNG is estimated based on timing. Specifically, the LRNG calculates the difference between the timings of successive events to estimate the entropy value. Here's the formula used to calculate it. The amount of entropy added is derived from this timing data. For instance, if we have consecutive events like key presses, the system measures the time between them and calculates the unpredictability of those timings. Let me explain this with an example. Suppose we have 3 events. First key press at time t1, which is 10 milliseconds. Second key press at time t2, which is 15 milliseconds. Third key press at t3, which is 25 milliseconds. Using the formula, we finally can get that delta 3 equals 5 milliseconds. Based on these calculations, the system estimates how much randomness or unpredictabilities exist between these timings. The more unpredictable the timing differences, the higher the entropy value. Now, let's move on to updating the pools. The LRNG uses 3 pools: primary, secondary, and random pools to store entropy. These pools are updated every time new entropy is added, either from external system events or from internal reseeding. Here's the pseudocode for how entropy is added to these pools using the Twisted Generalized Feedback Shift Register, also called TGFSR algorithm. This pseudocode shows how entropy is added to the pools. Here's a step-by-step breakdown of how it works. First, G is the new entropy word we're adding, and J is the current position in the pool. Then the result is further XORed with the lookup table. Finally, the updated value is stored back into the pool. This update ensures that the internal state of the pool remains unpredictable. Let's take an example to understand this pseudocode. Imagine we're adding an entropy value G equals 42. The pool is a 32-word array, and we're updating the word at position J equals 5. The function would take this new entropy value, XOR it with several other pool values at different positions, and then apply a bitwise shift and XOR with the table lookup. This ensures that the entropy is well mixed across the pool and is hard to reverse engineer. The final step in the LRNG process is extracting random bits. When the system or user requests random data, it extracts bits from the secondary or random pool. This process involves hashing the pool state and updating it with every extraction. This pseudocode shows the process of extracting random bits. It first computes a hash of a portion of the pool using SHA-1. The result of the hash is then added back to the pool. It does this multiple times, updating different parts of the pool. Finally, the output is produced by folding the hash results and outputting the random bits. This ensures that each time random bits are extracted, the pool is also updated to maintain unpredictability. For example, say the pool has 32 words and we need to extract 20 bytes of random data. The algorithm will hash the first half of the pool, add the hash result to the pool modifying it, then hash the second half of the pool and do the same. Finally, it will fold the output and extract the required number of bytes. Each extraction updates the pool, ensuring that future extraction produce different results, which is key to maintaining the randomness. To summarize, the entropy estimation in LRNG uses timing data to calculate unpredictability. Updating the pools uses the TGFSR algorithm to mix new entropy into the system. And finally, the extraction process ensures that random bits are generated securely and unpredictably. The LRNG works through three key stages. First, system events generate entropy. Second, the entropy is fed into different storage pools. And third, when random bits are requested, LRNG uses SHA-1 to extract random bits from these pools. However, the researchers found that LRNG doesn't provide proper forward security. If an attacker knows the pool state at time t, they can calculate the output generated from time t-1. This is a significant flaw. Let's use a simple example to illustrate. Imagine you have a deck of cards and you shuffle them at time t. If someone knows the order of the deck at that time, they could reverse the shuffle and figure out what the deck looked like at time t-1. The same thing happens in LRNG. If an attacker knows the state of the pool at time t, they can use that information to reverse engineer previous random outputs. How does this attack work? Essentially, the LRNG uses the extract algorithm to update the pool and generate random numbers. If the pool isn't refreshed with new entropy, an attacker can reverse the state of the pool by guessing certain bits. The research describes two methods: a general attack with an overhead of 2 to the power of 96 operations, and a more efficient attack with an overhead of 2 to the power of 64 operations. To understand this, let's break it down with pseudocode. In the LRNG, every time it updates, it mixes the entropy from different sources and computes a new state. Now, if an attacker has access to pool T, they can run the reverse of this function and guess what the pool looked like at t-1. By continuing this process, they can keep going back in time and find previous outputs. The key part of LRNG is the collection of entropy from system events, but the researchers found that the actual entropy is much lower than expected. For example, in an experiment measuring disk I/O events, they found that the system added about 1 bit of entropy per event, despite collecting 32-bit data. This means LRNG overestimates its entropy, which can weaken its security. Here's the problem. These events might not be as random as we think. Most of the system events fell within a narrow range of 77 to 82 milliseconds. The researchers found that the actual entropy collected is often lower than what LRNG estimates. This makes the random numbers less secure. Another issue with LRNG is that there's no limit to know how many random bits a user can request. An attacker could repeatedly request random bits, draining the system of entropy. Imagine a water fountain where everyone can take water, but one person decides to take it all, leaving none for anyone else. This creates a denial of service attack. The researchers demonstrated this by continuously reading from /dev/random and blocking other users from accessing random bits. To fix the forward security issue, The researchers recommend changing the order of operations in the LRNG. Currently, the pool is updated first, and then the output is generated. By switching this order, generating the output first, and then updating the pool, we can prevent attackers from reversing previous states. To avoid DOS attacks, the researchers suggest implementing a quota system. Each user would have a limited amount of random bits they can request at a time. It's like rationing water at a fountain. Everyone gets a set amount, so no one can take too much and leave others without. The Barak-Halevi construction offers a simpler, more secure design for random number generators. Instead of the complex layers in LRNG, this model separates the entropy collection from the random number generation process. Think of it like separating the ingredients and the cooking process in a recipe. First, you gather all the ingredients, and then you cook. This makes it easier to ensure each step is secure. The open source nature of LRNG means that anyone can review the code, but it also means attackers can analyze it too. The researchers suggest better quality control for cryptographic components like the LRNG. It's like a locking being public available for everyone to inspect. While this transparency helps identify weaknesses, it also gives attackers a chance to study and exploit vulnerabilities. In conclusion, the Linux random number generator is crucial for system security, but it has significant flaws, especially in terms of forward security and entropy collection. Here are the key takeaways. First is LRNG's forward security is broken, making it possible to reverse previous random outputs. The second is entropy collection in routers is weak, leaving them vulnerable to attacks. The third is DOS attacks can deplete the system of random bits. The fourth is simpler designs like the Barak-Halevi model could provide better security. By addressing these vulnerabilities, we can ensure more reliable and robust cryptographic systems in the future. Thank you for your attention.